Hi, we're Team SmartLot. My name is Mia Brown.
I'm Luis Alvarado.
I'm Fazan Bungish.
I'm Justin Matthews.
And I'm Joshua Vessel.
All right. So a little bit about our project background. So currently there's a lot of inefficiency when it comes to the parking process in open lots. And this inefficiency can cause excess carbon emissions, increased on-campus traffic, and then just general frustration for drivers on campus.
Going quickly over our needs statement, our solution needs to be able to reduce the time people spend searching for open parking spaces and also give users a detailed idea of where those vacant spots are located.
So being modeled after Kane Garage, we're making a hybrid system to both detect cars entering and exiting the lot and analyze the parking lot occupancy by means of a system of cameras. And this is to maximize the efficiency and accuracy of our design. Some of our main objections with this sort of hybrid system are to eliminate environmental and user errors while maintaining cost and convenience.
For our parking system, we have 4 requirements: profitable, easy to use and understand, scalable and efficient, and accurate information. So it needs to be profitable because it's important for users to be exclusive and to find unlawful users. Usability is important so that both users and client can easily understand the system. Scalable and efficiency are important to provide information at all times for the user. And accuracy is important so users can rely on the system rather than on chances. We also have 5 engineering requirements for our system. First, we aim to create a less expensive implementation of what has already been done in parking garages. The system's goal is to analyze a portion of a parking lot and help the users find the spots that are open through the use of a user-friendly GUI. Additionally, the system should provide accurate live information at any given time.
Okay, so last time we presented for our proposal presentation, we discussed the different kinds of sensors based on a report or article that we found. And we discussed the pros and cons of those, but ultimately we decided to go with the pressure sensor because it was the least intrusive when it comes to installing the sensors, and then it also is the best sensor for most weather conditions and most lighting conditions, or all lighting conditions. We decided to go with the Arduino rather than other microcontrollers because it's the microcontroller that me and Josh both have the most experience with for putting together sensors. And then also we decided to go with vinyl plastic tubing versus rubber tubing because the vinyl tubing was better for determining the difference between a car or someone driving over the sensor with a bike or walking over it.
For image processing, there were multiple options that I could have went with, and some of them are Skikit, Image, DLib, OpenCV, and we chose to go with OpenCV because it has basic image processing tools, and for this project, what I'm using image processing here means taking a picture and sending it to ML. So OpenCV does that very efficiently, where I could grab a picture of the live feed or a video, and I can send that to the machine learning process. And OpenCV has multiple interfaces. It has more programming function library. It has different community forums where people are very helpful. And if I had any questions, I can ask and they can answer it immediately. It also has vast algorithms that I can use if I wanted to make a picture clear or something like that, or smooth it up or something like that. Even though that's not in the scope of this project, if I wanted to do it, I could. and it has extensive use, meaning it has documentation available, YouTube videos, programs available online. So that would have helped me a lot.
So initially, I used YOLO V3 to recognize any vehicles that were in lot 104, but it was difficult to be able to tell where each car was within the image. So I'm planning on moving on to Mask RCNN. Mask RCNN provides what they call a mask, and it will give the pixel location for each bounding box of every object that it finds. So that way I can send over the information for the GUI and be used to display it on there. Additionally, it also gives the measure of how much a car's bounding box is overlapping a parking spot's bounding box. So through this, we can tell if somebody parked illegally, or to be able to just tell the user that those two spots are taken because of the illegal parking.
The level 0. So on basic level, we're gonna get an image and sensors that go through our system, and it will give us a lot occupancy and the location of available spots. Basically, we take a picture. Okay, next slide. So basically, a car enters a lot. It goes through the sensor. The sensor is going to tell the camera to start taking more pictures frequently, and then we send those pictures to the server, where it goes through the machine learning process, and then we display the open available spots to the user. It can be through a display system or a website. In level 2, a car enters a lot, and this is an Arduino-based pressure sensor. It's a pneumatic sensor, so if you go through this, it detects a car and it'll send a signal to the Arduino, which then sends it to the server. And the image processing component here comes in, and it'll start taking, once it processes the signal, it will start taking pictures every 15 seconds. So we have about 8 pictures for 2 minutes, and then those pictures are going to be sent to the machine learning system server that is going to go through and process all the image and find the open spot, and then we'll display our system, or the open parking spot.
So this is a sample finite state machine of the way our AWS server would interact with the Raspberry Pi and would interact with the Arduino. This is an example if it were to be a 1-minute cycle every time pressure is detected. So like Fazan said, as soon as pressure is detected, it'll move on to the image processing stage, where it'll wait 15 seconds between each round. If a new car is detected over the pressure sensor, it would restart the entire machine, no matter whatever state it's in. It would just restart the processing stage.
Okay, so as far as the work that we've gotten done so far for the sensors, we've assembled them and we've tested that they work independently of the system as a whole. And that's what I'm going to show here. So as you can tell, you can see that it detects when the car is running over the pressure sensor. And we decided to test it at varying speeds, and that you can see here. So yeah, and then the numbers that show are basically the PSI that's measured through the tube every time the car runs over the pressure sensor. So we did tests to make sure that the sensors are triggered only by cars. We didn't get good video of it, but the sensor can't be triggered by bikes or people walking over them. And then we show that the sensors work at varying speeds.
So right now, the sensors are completely exposed during testing. We still need to encase them so that they'll be protected from both the elements and like cars driving around so they don't accidentally just knock it over or drive over it. We also need to secure the tubing because you could see in the previous video that it was just kind of on the ground. But this should be trivial because like in previous like experiments, we just used tape, and so it won't be that hard to find a solution for that. We also need to get the sensor to work wirelessly. We didn't want to focus on that until we had the sensor software working. We'll need to purchase an additional module for the Arduino. It costs about $7, so we'll get started on that. And then in the next weeks, as we begin integrating our separate tasks, the sensor information will need to send image processing so that it can be triggered. And then that's it.
You can play a video. So for image processing, what I did was I used my webcam to take pictures at every 15 seconds, and I took about 8 pictures. So that would be over 2 minute span. I wanted to do this over the live feed, but it wasn't working. But just to show that how it's going to work and how we're going to have those 8 pictures that are going to be sent to the server machine learning part, and then he will use those pictures. So I just took 8 pictures through webcam to show my progress here. And as you can see in the video that I have 8 pictures here, and then on the right side is just me going through all the 8 pictures, and that's about it. That's my progress here for image processing. Work in progress, I have to basically do the same thing to a live feed or either a video or live feed, depending on whether the live feed is going to go up or not. And then I'm gonna get the signal from the hardware team and create a trigger for the camera. So once I get that signal, I'll start taking pictures, and then I'll send those pictures to machine learning part of the face, and that's about it.
I will be working with those images that I get from Fusan. So here's an example image of the parking lot that we'll be working on. At first, the machine learning program didn't recognize all of the cars within that image, but then I did some extra training on the system and threshold, and I got the next image right here. As you can see, there's a lot more recognition of the vehicles within the lot. It even recognizes truck and people, but that's not really necessary. There are a couple of vehicles that it did not recognize, the ones that are on the bottom left below a tree. That's something that I'm still working on. So I will attempt at recognizing those cars and getting more accurate information for those edge case errors. And I'm also trying to figure out a way to send the results of where these cars are within the image so that they can be processed onto the GUI. And then at the end of all of that, I want to work with the rest of the software engineers to put it all together.
So once the information is available to be broken down and passed over to the Raspberry Pi, our Raspberry Pi will process the information and display a GUI as shown to the users at the entrance of the lot. This will provide them both with a count of available spaces and a map to the available spots upon entry.
All right, so we have tested the sensor system pretty extensively so far. The tubing is pretty like stiff enough that just like a bike or a person walking over it, or even like a person like stomping on it, they can't really change the pressure that much. So it's pretty easy to set the limits so that only cars can be detected. We've been able to detect cars going up to 35 miles per hour, which we said was a reasonable limit to how fast someone might drive in the parking lot. And then we have not yet implemented the sensor triggering image processing yet. But we will do that in the future.
For image processing testing, there are three test cases that I was focused on. The first test case is where does the image processing software begin only when triggered. Like we don't want it to just start taking pictures randomly. So only when it gets triggered, it should take a picture. And then the second part is can the image processing software detect a trigger from the sensor? Do I get a trigger from the hardware component so I can start my stuff? And does it take a picture every 15 seconds after the trigger? I have that part done. I showed that with my webcam picture, so I just have to translate that over to a video or something once I get the trigger.
There are three test cases for the machine learning software. I am able to detect cars, but I have not been able to detect all the cars within the lot. And I have not been able to send any of that information over to the Raspberry Pi yet, but that is the next plan.
For the display, we have 3 requirements as well, testing requirements. We want to make sure that the display is actually showing accurate information. This is both on the accuracy of the machine learning and on the accuracy of like the breakdown once the data is actually transferred to the Raspberry Pi and processed. We want to make sure it's done in a timely manner. So we don't want to take 3 minutes to process one image after the data is passed to the Raspberry Pi. We want to make sure that it's very quick and responsive to getting new data. And then our last test correlates heavily to the marketing requirements. We want to make sure that it's actually useful for whenever people like drive into the lot, they're given information that benefits them more than if they were not given any information at all.
And for the overall system, we have three different things that we want to test. The first being whether or not the system actually follows the design specifications that we have for level 2, which you can see at the bottom. And then we also wanted to make sure that the system meets all of our design requirements. And we also want to make sure that our system can work seamlessly without much human interaction besides the initial trigger to start the process.
For our design demonstration plan, as you can see, there's a camera right here, which is going to give us the live feed. And the red just means that it's occupied and the yellow is vacant. So the way it's going to work is there are 2 entrances. Let's say a car enters from this side. It will go through a sensor, which is going to trigger the camera to start taking pictures, or my program to start taking pictures of that live feed. And then I'll send those pictures to the ML program, which is going to go through it, and it'll find which spot was taken or which spot is still vacant. And after that, it will go through just in phase where it'll display the GUI. And there are 2 display boards. There's one right here, and then there's one right there. So as you can see, the red means it's occupied, and the greens are sensors, and yellow is vacant. So this is how we were going to test our program.
So as far as project management goes, I'm the team lead, also working on hardware. Josh is working with me on hardware, and Luis is working on software, mostly the machine learning. Faison is working on software, mostly the image processing, and then Justin is also working on software, mostly the front end and displays. Here is our schedule of tasks, and you can see on the right-hand side what we have completed so far. And then this is just a Gantt chart visualization of that.
For our economic analysis, it remains the same as last time. Just one detail is the minor maintenance is probably going to refer to just the tube over time. Right now it seems fine, but it's likely that like over years, the tubing could wear down.
Here is our current budget for the parts that we've changed since the last presentation.
Our societal, safety, and environmental analysis factors remain the same as last time. Societal, users might experience minor reduced privacy due to the camera system. Safeties, drivers will not be endangered by the system because all the equipment is planned to be pretty out of reach. And then environmental, it'll cause a reduction in CO2 emissions.
Here are our references and then some of our acknowledgements. We want to acknowledge Julie and Dell from Tamu Transportation, who have helped us a lot on the administration side, and then as well as JD and Carl for their input